In our final section, 11.5, we're going to find the probabilities of independent and dependent events. So our key learning objectives are exactly that. What are the probabilities of dependent and independent events? So we need to know for our vocab what are independent events, what are dependent events, and what is this thing called conditional probability. So taking a look at these, two events are independent events if the occurrence of one event does not affect the occurrence of the other, and the events are dependent events if the occurrence of one event does affect the occurrence of the other. So if we look at this, a jar contains red and blue marbles. I randomly choose a marble from the jar and I do not replace it. Then I randomly choose another marble. Tell whether the events are independent or dependent. Well, these are dependent, okay, because once I select a marble and pull it out, if I don't put it back, now the environment of the jar has changed. Okay, so for example, in event A, the first marble I choose is red. That means that when I calculate, the probability would have been, the color over the total number of marbles. But by the time I select my second marble, the total number of marbles is less by one marble. And also the total number of red marbles is less by one marble. So the circumstances have now changed. So when I calculate the probability of event B, I have to take into account what changed about the jar when I had event A. Okay, so that's a good example of a dependent event. The probability that B occurs given that event A has occurred is called conditional probability of B given A. So it's conditional, meaning I have to know what happened in A in order to calculate what happens with B. Okay, and this is how you would notate it, is you would do it B with the vertical line A, and this is red, the probability of B given A. Okay, note that A and B are independent events if and only if the probability of B is equal to the probability of B given A, since the probability would not change. Okay, so that's a little technical, but if we want to talk about independent events, the probability of A happening and then B happening is the probability of A times the probability of B. This is for independent events. And for dependent events, it's the probability of A happening times the probability of B given that A has happened. Meaning we have to take into account A when we calculate the probability of B. Okay, and this can go on to 3 events, 4 events, 5 events. When you have multiple events, you have the probability of each event times each subsequent event to get the probability of a sequence of things occurring. So let's take a look at how that looks. As part of a board game, I need to spin this spinner right here, and it's divided into equal parts. Find the probability I get a 25 on my first spin and a 50 on my second spin. Now, will the spinner change based on my first spin? No, it will not, right? Everything's still going to be there. So the probability of getting the 25, you can see it's in 8 sections, is 2 out of 8, or 1/4. And because there's no change, I know that the probability of getting the 50 is 1 out of 8. There's 1/50 out of the 8 chunks. So the probability of one thing followed by the other is 1/4 times 1/8, which is 1/32. That's the probability of spinning a 25 followed by a 50. Okay, a bowl contains 36 green grapes and 14 purple grapes. I randomly choose a grape, eat it, and then randomly choose another grape. Find the probability that both A and B will occur. Well, this is going to be a dependent event. So if the first grape is green, right, there's a total of 50 grapes. So the probability of the first grape being green is 36 out of 50, right? And the second grape, well, there aren't 50 grapes anymore. I ate one. There are only 49. And there aren't 36 green grapes anymore, there are 35. Okay, so I'm going to simplify my fractions. And I see that, let's see, this will be, if I divide that in half, this is going to be 18/25. And I can factor a 7 out of each of these, so this will be 5/7. When I multiply them, the 5 goes into 25 5 times, and I get 18/35 is the probability that I will select a green grape followed by a green grape. Okay, so when I calculated B given that A had happened, I had one less green grape and one less total grapes. Okay, continuing on with these examples. I can rewrite the formula for dependent events on the first page of the lesson to give you a rule for finding conditional probabilities. So the probability of B given that A has happened is the probability of A and B happening divided by the probability of A. And if we want to take a look at this, the table shows the number of tropical cyclones formed during the hurricane seasons from '88 to 2004. Use the table to estimate the probability that a future tropical cyclone in the northern hemisphere is a hurricane, and B, that the probability that a hurricane is in the northern hemisphere. Okay, so the probability of A, right? So A is the future tropical cyclone is actually a hurricane. Okay, so I have to find out all these different storms. It would be nice if I had totals here, but I don't. So when we look at the hurricane, it's going to be 545. 545 divided by the total number of these. So let me get the total number. So I'm going to have 199 plus 398 plus 545. So that's 1142. So there are 1142 tropical cyclones. 545 of them are hurricanes. That's the probability of A. So what's the probability that the hurricane is in the northern hemisphere? Well, that's going to be 398 out of 598. So I'm sorry, hurricanes. I was doing tropical storms, my mistake. So it's going to be 545 out of, let's see, that's 760. So the probability of A in this case is 545 divided by 1142, which is basically 0.477. Or 47.7%. And the probability of B is 545 divided by 760, which is 0.717, or 71.7%. Okay, more interest in independent and dependent events. I randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card is not a heart and the second card is a heart if I replace the first card before selecting? So let's just do A. So if I put it back, that's going to make this an independent event. If the card gets put back in it, then the deck hasn't really changed. So the probability of the card not being a heart is 39 out of 52. And the second card being a heart is 13 out of 52. Okay, so if I wanted to go ahead and simplify this, 13 out of 52 is basically 1 in 4. And this is 3 in 4. So 3/16. And I'm going to go ahead and make that a decimal because that may make it easier to compare. 0.1875. Now B, these are dependent events. If I don't replace the card, this is still the same. The first is still the same, but now there are still 13 hearts in the deck, but there are only 51 cards. Okay, so this is distinctly different. So 3 goes into 51 17 times, and I'll get 13 divided by 4 times 17, which would be 68. So if I get 13 divided by 68, that's 0.1911. So you can see in the dependent event, it's a little more likely to happen. But that's because this non-heart got put back into the deck. And that's what caused the difference in the probability. Okay, and finally, using observations made of drivers arriving at a certain high school, a study shows that 69% of adults wear seatbelts while driving. A high school student also in the car wears a seatbelt 66% of the time when the adult wears a seatbelt, and 26% of the time when an adult does not wear a seatbelt. What is the probability that a high school student in the study wears a seatbelt? Okay, so this becomes complicated because the probabilities are different based on what the adults are doing. So this is another good spot to use this sort of event tree. So the first part is for the adults. Okay, so the adult is 69% wear the seatbelt, which means that 31% don't. So the student wears a seatbelt 66% of the time when the adult wears, which means then that 34% they don't. And when the adult wears the seatbelt, doesn't wear the seatbelt, they only do it 26% of the time. And down here, that means that 74% of the time they don't wear. So remember, this is do, and this one is do, and those are the ones I care about. These here are don't, right? This is do, don't, and this one is don't. So if I want to find the probabilities, in fact, this is really valuable when somebody wants you to be able to tell the probability of everything that might occur. So if I want to know the probability that the student does wear the seat belt when the parent does, it's the probability that the parent does times the probability that the student does, and that's 0.4554. So it's 45.54%. If we go the other direction, and I'm going to calculate them all because I want you to observe something. So 0.69 times 0.34, that's 23.46%. If I'm not wearing the seat belt, that's 0.31 times 0.26 is that the student wears when the adult doesn't. That's 8.06%. And now neither person wearing the seatbelt, 22.94. And if you look at these two are going to add up to be the 31%. and these two are going to add up to be the 69%. And the whole thing adds up to be what? 100%. So our probability is that a student wears a seatbelt is going to be this one plus this one. Those are where they do wear the seatbelt. So we're going to have 0.6, 0.54 plus 0.06 is 0.6, and then 45 plus 8 is 53.60%. Okay, so this is using a probability tree or an event tree to go ahead and calculate the probabilities of all the different outcomes. Okay, and that's the conclusion of our section in Chapter 11.